Sweet.
Okay, well, thanks a lot. So maybe the first thing I should say is to define the word magic, because you're probably wondering, what do I mean by that? So it's pretty simple. If you find some kind of cancellation or maybe a structure, and it looks like that structure should have a symmetry explanation, but you don't actually know what the symmetry explanation is, then we'll call that magic. So today's magic will, of course, one day be old hat, but at least today it's magic. And I'll be talking about work that was in the following set of papers with various collaborators, including people who are here in the audience. Is John Joseph Carrasco, Josh Noley is here somewhere. And this includes some work which still is unpublished. Maybe it'll be another month before we have the paper out. And I'll be talking about three topics. So one is pretty old. Maybe many of you have heard about it, is this duality between color and kinematics. Certainly this is something that counts as magic. And then I'm going to show you other magic. And that's examples where you find that what look like are valid counter terms, but they have zero coefficient. So that's definitely in the class of magic. And then the third bit of magic, which is actually from the forthcoming paper, has to do with cases where we know about the divergences. So there's two examples in pure, either supergravity or pure gravity, where we actually have divergences. The pure gravity divergence is well known for more than 30 years. It's just a two-loop divergence. But I'm going to show you that it has a very curious structure. It looks like it has to do with anomalies. Okay? So first, let's get going on the duality between color and kinematics, because that's going to play a role in the way the surprises with the ultraviolet finiteness. Okay? So let's just look at a three-loop diagram. And let's just write down just an example. Okay, and then let me mark a leg. Let me mark this one. Mark that one, mark this one. And then let me circle this. Like so. And then maybe let me put in a minus sign, and let me write equals 0. And this is a formula for color. So this is, if you look inside the circle here, you'll recognize just the color Jacobi identity. So for color, so if these were just pictures for color factors, then you'll say, oh, this is just a trivial formula. It's just the Jacobi identity. And in fact, it is trivial. Okay? So let's now write down a formula for an amplitude. Just a generic formula. So I'll write a Yang-Mills amplitude at multi-loop level the following way. We're going to sum over diagrams. And these diagrams we're going to make in one-to-one correspondence to the color factors. So if I happen to have a diagram that has a contact term, what I do is I identify in here a color factor that looks like this diagram. And I just kind of explode it out, multiply and divide by whatever propagators I need, or inverse propagators. Okay. So this would be the sum over, this is cubic diagrams with cubic vertices. Okay, and then we're at loop level. So let's just ddp over 2 pi to the d. We'll do this in d dimensions. Okay, so there's L loops. And then let's put in the color factor. The color factor you read off just from the pictures. Let's put in a numerator factor This you can somehow get out of Feynman diagrams. So this is the kinematic part. Or kinematic numerator, let's call it. Okay, and then maybe you need some symmetry factor. So this could be a 1/2 or 1/4. And then let's put in the Feynman propagators. So this is for diagram J. So these are just Feynman propagators. Okay, and
as you define it, it's not unique, right?
It's not unique, right? The constraint is that the amplitude be correct. But what exactly I do here is definitely not unique. Okay, and
that step there, like the convective.
Yeah, exactly. You can you can use colored Jacobies to start moving things between diagrams. So it's definitely not unique. I didn't even tell you that this thing is local, so you can even make that non-local. Okay. So there's a claim. This is from our paper. So this is a conjecture. So this we don't know if this is true in general, but we certainly know it's true in certain cases. There's a claim that there exists a way, related to David's comment, that there's an ambiguity in what these numerators are. There exists a way such that for every colored Jacobi identity, Ci plus Cj plus Ck equals 0, there exists some numerators constrained to give you the correct amplitude, such that the same Jacobi identity is satisfied. Now, presumably there's some symmetry understanding for this. Clearly, it looks like there's an underlying infinite dimensional Lie algebra. I don't know if Donald will say more about that in his talk. But there's clearly some symmetry explanation. It's fair to say we don't have a proper understanding of this. But, of course, that shouldn't stop us. Just because we don't understand it doesn't mean that we shouldn't use it. And the way we use it is the following. Once you've done this, so let's suppose that you're able to make this rearrangement in some case. Let's say like 3-loop n equals 4 super Yang-Mills, or 4 loops, or other cases. Let's say you're able to do this. Then the claim is that if we want the corresponding gravity, so if we go between gauge theory and we want to go to gravity, all we do is we take the color factor and we replace it with a numerator factor, where these numerator factors obey the same algebra as that. So what I do is I come over here, I call it gravity, and then maybe let me put a twiddle over one of these, because maybe these aren't even from the same gauge theories. Maybe one is n equals 4 super Yang-Mills and the other one is ordinary Yang-Mills. Okay, and the claim is that this is now a gravity amplitude. I think you'll agree that the word magic is appropriate. Okay.
What's the status of seeing this come from the Lagrangian or from some structure?
There's definitely been quite a bit of work. Can I actually toss? Will you talk in any way about this?
Yeah, I probably will talk a little bit about this.
Yeah. So maybe you should just wait until his talk. So he's going to talk about it. It's definitely not perfect, although there's quite a bit that's understood. Okay. And in fact, what we're going to do, we're going to just look at some simple cases, like if I want n equals 8 supergravity. I'm not going to really talk much about this theory, but the way we get it is we take n equals 4 super Yang-Mills times n equals 4 super Yang-Mills. Okay. Now, I will talk about n equals 4 supergravity. So one construction you can do is you can take n equals 0 Yang-Mills, just pure Yang-Mills, times n equals 4 super-Yang mills. And you have n equals 4 supergravity. Or also n equals 5 would be another one I'll mention in passing. Well, you can guess exactly what it's going to be. N equals 1 super-Yang mills times n equals 4 super-Yang mills. And there's actually now quite a few constructions of different supergravities, much more sophisticated than just these simple cases. Okay. So let's look at an example. So let's do n equals 4 supergravity at 3 loops. Okay? And let's have a look at the structure of it. And that'll bring me to the second case of magic, which is the ultraviolet properties. So at 3 loops, I'm going to pick the ladder diagram. Let's see, another copy of the ladder. We're really just looking at the numerators. There's only one copy of the denominators of the propagators. But so this copy, let's say we'll make this one ordinary Yang mills. So this is ordinary Yang mills. And you can use any reasonable representation. It turned out we used Feynman diagrams, which is maybe a little embarrassing in this day and age, but still, that was a reasonable representation for what we needed. But the second copy, you have to use. It says right here, I have when I make this replacement, I have to have the algebra the same. So for that, we need what's called a BCJ representation of n equals 4 super-Yang mills. And this one, it just happens to be, is a very simple numerator. It's s cubed t a tree. It's the 4-point tree. So it looks non-local because there's a 4-point tree here, but there's these factors that eat the propagator. So this is actually completely local. And this happens not to depend on loop momentum. So it's particularly simple. So now let's do a little bit of counting.
I'd like to ask a question.
Sure.
You have the sum of all cubic diagrams.
Right.
So the magic only works after you perform the sum, right? Or individually?
Well, to get the correct amplitude, of course, I have to sum over all of it.
But the magic works?
Yeah, it's diagram by diagram.
Diagram by diagram.
I mean, I make the substitution. I instantly convert this diagram. Maybe you're referring to here. So if I want the supergravity, what I do is I take this diagram, I write down the color factor, and I take this color factor, let's call this diagram 1. I take the color factor 1, and I go s cubed t a tree, and that's the diagram for supergravity, just like that.
So it's diagram by diagram.
Diagram by diagram, right. That's actually important for what I'm going to say because we're going to do some power counting. Okay, so let's look at ordinary Yang mills, and let's just find one term that's interesting. So I had one term for ordinary Yang mills, so we'll call it like n equals 0. Yang mills, the numerator of it. There's one term in there that looks like this. Well, it's actually, 5, 6. Epsilon 1 dot L5. So it's just the dot product of this polarization without momentum. There's epsilon 2 dot L5. So it's this one dotted with that, or actually one of these momenta, but I'm only caring about the leading behavior. So the leading and loop momentum. Then there's epsilon 3 dot L6. There's epsilon 4 dot L6. And then you can see that there's more vertices that carry loop momenta. And in fact, there's a term that looks like L5 dot L6 squared. Okay, so you can count that there's 8 powers of loop momentum here. Okay. So this one term has 8 powers of loop momentum, and there's many other terms. But one thing you'll notice about this term is it does not have an inverse propagator. This is what's called an irreducible numerator. And then these momenta are dotted into the external polarizations. So you can't cancel any propagators. So this does not mix with other diagrams. And we only have Feynman propagators, so we're thinking about it covariantly. Right? So there's a term in here that's poorly behaved. Okay? And it behaves like L to the 8th. And in fact, if you were to take this one term and integrate it, you'll find, sure enough, it diverges. That should not surprise you, because ordinary Yang-Mills is log divergent. And we can just do our little counting. So there's an L to the 8th. Comes from this side. From this side, only external momenta. So we have D4L, 3 loops. There's an L to the 8th. And then you can count up 1, 2, 3, 4. Anyway, there's 10. So L squared to the 10th. And then you see this is log lambda. Okay. So what I've just proven to you is there exists a term in this amplitude of n equals 4 supergravity which is divergent. And there's nothing you can do about this. You can't mix it with other diagrams if you keep the diagrams covariant, meaning only ordinary Feynman propagators. So let's just make a definition. So let's just say that this amplitude happens to be finite, which of course it will be. I mean, we know, but let's just say, suppose the sum over the diagrams is finite, is UV finite. That's a curious phenomenon, but let's give it a name. So we'll call that an enhanced cancellation. And in fact, it is finite. We calculated it. So that's this was done with Scott Davies, Yutun Wang, and Tristan Denon. It is finite. Or n equals 4 supergravity at 3 loops and d equals 4. It is finite. And to make the story even more interesting, despite some valiant attempts from my friends Kelly Stell, Guillaume Bassard, and Paul Howe, there's still no explanation from this according to standard symmetry. So, in fact, that definitely is exactly what I mean by magic.
So that means there is a counter term?
There is a valid counter term. It's an R to the 4th. Or there is one that looks valid. I don't know if it actually is. Maybe there is some symmetry explanation. But as of this minute, there is no symmetry explanation. Just bits and pieces. It's an R to the 4th counter term. It has a coefficient of 0. Okay. And in fact, this isn't the only one. We have plenty of examples of this now. By the way, this one is equivalent to n equals 8 supergravity at 7 loops. It's in the same class of divergences. And in fact, we have examples.
It realizes different symmetries, right? It realizes different symmetries. I mean, the two theories are different.
Which two theories?
N equals 8 and n equals 8.
Yeah, but it's in the... Yeah, that's right. It's different symmetries.
So, for example, in n equals 8, you need the E77. You don't have the structure of the salt theory.
Well, well, we can discuss it later, but it's definitely in the same class. So when Michael Green does it, he only uses supersymmetry.
But supersymmetry is not no. Okay. Well, anyway, yes.
No. That's actually well, we'll discuss it later.
Well,
it's definitely unexplained, and if you want to change that, be my guest.
I want to understand the details.
Yeah, it's definitely unexplained as of this minute.
The n equals 8 version is explained?
No. N equals 8, unfortunately, is still open.
Okay.
No,
it's an open question.
That equivalent term, I to the 4, is not there in n equals 8. I'm gonna say no.
Right.
Yeah, good.
Right, it's a different counter term. In n equals 8, we're talking about a d6 r to the fourth. Okay. There's an analogy. Okay. Yes, examples. So in fact, we now have quite a few examples of this phenomenon. So you might say, okay, maybe this is some kind of an accident, but in fact, we have good examples. So one of them I already mentioned, n equals 4, L equals 3, D equals 4. Okay, then another one would be n equals 5, L equals 4, D equals 4. That's also an interesting one. There's a very good one, which I'm not going to have time to talk about, but that's actually quite an easy one to analyze, which is, let me write it as Q equals 16, because I'm going to switch dimensions to D equals 5. So I mean half maximal supergravity, so it's the same as this, but if I use n counting, that depends on what dimension you are. So let me just count supercharges. Half maximal supergravity at L equals 2. That's another good example. And this we actually understand quite a bit about. But unfortunately, I don't have time to discuss that, because the example I want to talk about is one that is very well understood, that has been studied 30 years, for more than 30 years, which is pure Einstein gravity. This is magic. Here, at least the lack of the one-loop divergence we wouldn't call magic, because we understand this very well. That was understood by 't Hooft and Veltman.
Okay. Can you draw the diagram for example 4?
Yes. So for which one?
For that one.
So it'd be some 2-point. It could be a diagram, something like this. Would be the counter term. We're going to talk in detail about this counter term, because this one I want to look at more carefully. Because the claim is that there's a general pattern here that this will be part of. And the good thing is this one we know a lot about. Another good thing is we're going to be talking about relatively low loop orders. We're talking about 1 loop and 2 loops. So then that makes the analysis a lot simpler. So then it becomes possible to understand what's a little bit better what's going on here. I should also mention there is a divergence in n equals 4 supergravity, 1 higher loop. But I'll come back and I'll discuss that in the context of what's happening here. Okay. So this is actually another example of an enhanced cancellation. I mean, you might call it trivial, but it's definitely, according to the definition I said, because I can just draw a diagram. Okay. So there's not going to be any surprises, because, like I said, 't Hooft and Veltman understood this quite a long time ago. But let's just have a look at it in the context of these enhanced cancellations. So I can identify some term which is very badly behaved, that doesn't mix with any other terms. Let's say at 4 points, I can look at this 4-point diagram. I would write down, there'd be the polarization tensor, L mu, L nu. Let's make 4 of them. So I just mean these 4 legs. Okay, so you see it goes like the 8th power. So you can just do the power counting. Also, you see this is not inverse propagator, so it doesn't mix with other diagrams. Okay, so we can write down d4L, L to the 8th, L squared to the 4th. So this is very poorly behaved. Okay, and this is an enhanced cancellation. But you'll say it's a trivial enhanced cancellation. And the reason why you'll say that is you'll remember the Gauss-Bonnet theorem. You can write down the available counter terms. You might write down R square. You might write down R mu nu square. So these are let me just write CP for counter terms. And then Riemann. Now, these two we can cross out because we would say, by the equations of motion or by making a field redefinition, we can remove these terms. So the only possible one that's left is Riemann. But then you will remember the Gauss-Bonnet theorem. You'll remember the Gauss-Bonnet theorem, and the Gauss-Bonnet theorem says that integral d4x, notice I put it in 4 dimensions, square root of minus g, and then it's a particular combination r mu nu square plus Riemann square. That's equal to 32 pi squared times the Euler characteristic. So this is a topological quantity. Now let's suppose we're in flat space. Then you would say, oh yeah, I see what's going on. Because this is 0 in flat space, then obviously I can replace this by these, and these already vanished. Therefore, there's no available counter term. And Tufton-Beltman, of course, understood this.
You meant asymptotically flat.
Asymptotically flat, yeah. And in fact, you'll probably say, oh, what's going on here is an accident. It just happens to be that there's a Gauss-Bonnet theorem that happens to come in exactly at the first loop order. And that's the end of that. And in fact, if we look at the literature, you'll find there's a paper, Goroff and Sognati, and then there was also Van de Ven, where they went to look at 2 loops, and they discovered exactly what you might expect. They found that there's a 2-loop divergence, which, let me write it in some corner so I don't lose it. If I write it here, let me put it over here. So Goroff and Sognati found that the divergence at 2 loops is 1 over 4 pi squared. Should be 1 over 4 pi to the 4th. And then there's a number 209 over 2880, and then 1 over 2 epsilon, and then it was 3 Riemanns stuck together. It had to be Riemanns, of course, because if it was Ricci, then it would vanish. It wouldn't be a valid counter term. So let's make it alpha, beta, gamma, delta, rho, sigma, and then alpha, beta. And presumably, like the rest of the world, you would have said, see, there's nothing going on here. This was clearly just an accident, whatever happened at 1 loop. But I'm going to argue that it's not that simple, that in fact, this is not a generic divergence. It's very special. And it's actually has a lot to do with what's going on at 1 loop. Okay. So first thing is, let's put this into a non-trivial space.
It has, the 1 loop is so obviously the name because you don't get a 1 over epsilon squared.
But it's much more than that. You're about to see, yes, right, and not in a trivial way, but absolutely. The fact, as David observed, the fact there's a 1 over epsilon here is, of course, tied to the fact there was no 1 loop divergence. So you get a 1 over epsilon because that's just the first divergence.
2880?
Yes, 2880.
So why don't you divide both numerator and denominator by 3?
No, it's 209.
No, 209. These are prime numbers. This strange prime numbers. Don't ask me where those prime numbers come from. Okay. Now let's put this into a non-trivial topological space, chi non-zero, or maybe we'll use dimensional regularization, so we're not in 4 dimensions. Then, in fact, we can write down what the divergence is. And that's 1 over 4 pi square, and there's a 53 over 90 epsilon. We have d equals 4 minus 2 epsilon. Okay? And that's the one-loop divergence. We can give this a name of an evanescent operator, because it's not there in d equals 4. It disappears. But it kind of wants to be there. Right? Okay. Now, this number, that number is the trace anomaly. Actually, the trace anomaly comes with many names. It comes with a name of conformal anomaly. Maybe I'll call it the conformal anomaly, the Weil anomaly. And it's been studied in great detail by many people. Maybe some people here in the audience studied this. So this anomaly, this is not in symmetry of the Lagrangian, because notice I called it the conformal anomaly. Gravity, of course, is not conformal. But on the equation of motion, there is a scaling symmetry. Okay. But the key is that this has to do with an anomaly, this number. Okay. Now, let's start poking at this divergence here. So this divergence, you might have said, oh, it's some very generic divergence. That the reason why it diverges is because we just power count, and that's the end of that. And there's nothing really subtle happening. I think that's the accepted wisdom. But let's just notice something about this particular operator. This particular operator, the r cubed, so let's put an r cubed here. It only wants identical helicity. So let's stick that into a 4-point where I have an amplitude, because I like to work with amplitudes. Then there's 2 configurations where you can get a contribution. So there's my r cubed, so that's plus, 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 and then you can have plus, minus, like that. And the contribution, this one, something like this, where there's minus, 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 and plus, plus, this one is just not there. Okay. Now, once you know that, then, in fact, it's easy to see that there's something special going on with this divergence. That this divergence that we see at 2 loops is not generic. So let's have a look at a 2-loop diagram for 2-to-2 scattering. And we're going to focus on this one. This one we've worked out, this helicity configuration. It turns out this helicity configuration is, I don't know, thousands of times simpler than this one, which is then thousands of times simpler than that one. This helicity configuration, the final answer for this 2-loop expression is just a few lines. So this is a good one to study.
This is the maximally violated?
Yeah, this is the maximally or beyond maximally. Normally people would refer to this as maximal helicity violating. Okay, this is like...
Your convention.
They're all incoming? They're all outgoing. Yeah, but anyway, they're all the same. Yeah, so it's the one that is 0. This one is 0 at tree level. And that's actually going to be an important point, because let's look at the unitarity cut of this.
0 at tree level. Oh, you mean the
zero
at tree level. Okay.
Tree level. So tree level. We're about to see that. So, in order to get a non-zero cut, so I'm not looking at the unitarity cuts, I have to have minus minus. Right? And this would be what people normally call maximally helicity violating. I mean, what they mean is at tree level. This is the maximal one. Okay. Now, because I have the all outgoing convention, when I flip, here it's outgoing. So if I continue, well, then it's incoming. So I flip it over. So now I need minus here. I need plus here. And then you notice the last tree is just identically 0. So the cut vanishes. So if I were to work out the divergence of this object in 4 dimensions, I would find that it's 0. not only because the divergence is 0, but because the amplitude is 0. In fact, the integrand, this integrand, it has a behavior. Let me take the loop momentum. So there's some loop momentum here. So now I'm off the cuts, but anyway, some loop momentum. And there's a 4-dimensional piece. And then let's call it mu. That's the minus 2 epsilon dimensional piece. This amplitude, this integrand, not on the cuts, but I just mean what the answer is, it goes like mu to the 8th. So it wants to be 0 very strongly. Okay? Now, where's the UV divergence? There is a UV divergence in here. And the way this UV divergence comes about is because at 2 loops, there wants to be a 1 over epsilon squared divergence. I have something that's vanishing as epsilon goes to 0. And when you actually do the integrals, you find it's of order epsilon. So it behaves like 1 over epsilon. And that's, you could say, a reinterpretation of what we see here. But the striking thing about this is that all of this looks like it comes from an anomaly, a 0 over 0 behavior. Now, I'm not going to prove to you that it comes from an anomaly, but I'm certainly going to show you that some parts of this number definitely come from that anomaly, trace anomaly. And in fact, we think all of it comes from an anomaly. We just have to name the anomaly. It's not the normal anomaly. I don't think it's going to be a symmetry of the Lagrangian, but it's going to be in the same class as the trace anomaly. But that's already very striking. Right here, this fact here, that the integrand, for this identical helicity, it goes like that, immediately tells you that this is not a generic divergence. There's something very strange about it. Okay, so let's actually do some numerology. I can show you where this number arises and what it has to do with the conformal anomaly. So when we first worked this out, we worked out the integrand, we integrated it, we grabbed the ultraviolet divergent part. How you do that in the presence of infrared singularities is some interesting story about that, but let me just say that we did it. So if you grab the bare part, let's just call it bare. You might be wondering why I'm calling it bare if there's no one loop renormalization, because it was finite at one loop. But let me call it that anyway. You discover that you don't get the right number. You get, instead of that 209, you get 3431 over another number. There's actually a difference between these two numbers. I'm looking at an amplitude here, and this is the counter term, but some simple combinatoric factor. You can be sure it doesn't involve 209 and 3431. Okay. Over epsilon. Okay, and then times whatever it needs, the appropriate kinematic factors to coming from the R cubed counter term. So in fact, it's the number and it's proportional to the appropriate R cubed counter term and other diagrams that go with it. So this was, of course, a little bit of a mystery to us, but it didn't take long. At least once we had great confidence in this number, then it definitely didn't take long to figure out what was going on. What was going on is there's another contribution. It's from our friend, the evanescent operator. So there's Gauss-Bonnet. Well, let's include him as the counter term. This gives a number 689 over 675 over epsilon, again times that. Anyway, you can do the arithmetic. the minus sign there. You'll see it is not, again, the 209. But if you think about it just a little bit more, there's a double counter term, because these are not one particle irreducible diagrams. So by GB, I mean the Gauss-Bonnet term. It's that counter term with that number. It's 53 over 90. And that number is 5618 over 675 over epsilon. Now you can do the arithmetic, and it's going to add up to 209 over 24 over epsilon. That's the same as this number once you account for the fact that we have an amplitude, not just the r cubed operator. So what this shows you is the conformal anomaly. You can see its effect in the divergence. Okay, there's also other pieces which we're not assigning to the conformal anomaly, but we're assigning to, call it anomaly-like behavior. And in fact, let's just say it's tempting to conjecture that this thing wants to be finite. It's just being blocked by an anomaly. And there's more interesting things about anomalies.
So what do you mean it wants to be finite?
Well, I'm about to explain that.
I mean, wouldn't it, if it wanted to be finite?
There's an anomaly which is stuff.
Wouldn't the Bayer term be zero?
No, it wants to be finite in the sense there's an anomaly. There's a symmetry of the classical equations of motion. There's an anomaly, like this thing here, which is blocking it. And it turns out, actually I'll get a little more precise about what I mean by it wants to be finite. Okay. It turns out this anomaly has its own anomaly. So it's like anomalies on top of anomalies. So if you look at the contributions to the trace anomaly from different particles, you see something very strange. And this has also been known for quite a while, although there's been, let's just say, murky literature where people argue one way or the other about the physical meaning of this. But let's write down some numbers now for the conformal anomaly. So this is a one-loop effect. Okay. So if I have a graviton, let's call it G, then it has a number 4 times 53 over 360. So now this is for the Gauss-Bonnet term, over epsilon times Gauss-Bonnet. There's some 4 pi's and things, but never mind. Anyway, it's got this number. There's the 53. And then if we look at a scalar contribution, so now we have 4 gravitons on the outside, scalar around the loop, then you get another number, 1 over 360, and then, of course, times the Gauss-Bonnet. You look at the antisymmetric tensor. You might recall the antisymmetric tensor is dual to a pseudoscalar. But no, that number is unbelievably 91 times bigger. Okay, and needless to say, this caused a bit of a stir in the literature. And then, my favorite field of all is the 3-form. Because the 3-form in 4 dimensions has no degrees of freedom. Right? So there's nothing there. But, of course, it has a contribution, a very big one. It's got a minus sign, probably good, over 360, epsilon, and then Gauss-Bonnet. So nothing, in a sense, at least if you're taking a duality transformation of this in d equals 4.
Which you can't do. You're working in d dimension.
Right, that's why there's a contribution. That's why it makes a difference.
Right.
But at one loop, this doesn't make any difference whatsoever because all of this is evanescent anyway. Okay. But of course, what happens is at 2 loops, it makes a difference. So, for argument's sake, let's just say I feel like monkeying around with Einstein gravity and I want to add nothing to it. There. Then you can bet your last nickel that the divergence, the two-loop divergence, changes. Okay. And when you look at, so the basic, and also we've...
You're using some fine rules here. Is that just a perturbation about flat?
Yeah, I'm just doing perturbation. It's perturbation around flat space. Right. So, so a lot of the literature, actually, the confusion comes from the fact that people would look at one loop and say, "Oh, there's nothing going on. You know, this stuff is just confusing you." And it's true at one loop, there's really nothing going on at the end of the day because if you go back to d equals 4 for the operator, there's nothing there. But at two loops, that's where things start happening.
Is it true that we always get Gauss-Bonnet, no matter what is the matter content?
Yeah. I mean, it's the only operator you can write down. Well, it's really Riemann square is the only operator, but anyway, these are kind of trivial. You get a divergence. The divergence by the normal, principles of quantum field theory has to be one of the local operators. This is the only local operator you could write down.
Yeah, but what I mean, if you were not in flat space-time, it would not be a trivial.
Oh, you can. There's other things you can get. Well, there's certainly. Well, obviously. One thing.
For your purpose.
So right here, when I add this, there's another divergence. So there's a when you have this or this, there's a divergence. Like here would be a d phi to the fourth divergence. Mm-hmm. So there are other divergences around. Yeah. But the key point is that there's some control over the divergences that have to do with exactly what you're picking, like what duality transformation you've picked. And this has a lot to do with supergravity. Maybe one more point I should make. So we've checked carefully that at two loops, the divergence structure, whether you have an antisymmetric tensor field or a scalar, you get a different divergence. At one loop, it doesn't make any difference, but that was shown by Peter van Evenhuizen and other people. At one loop, there's no difference between these two, but at two loops, it definitely makes a difference. Now, what does this have to do? Okay, so immediately you get an idea about monkeying around with pure gravity, maybe with this. And also, let's look at n equals 4 supergravity at 4 loops, yes?
How did you compute those numbers?
How did we compute it?
Yeah, how did you compute those numbers?
Just from standard unitarity cuts.
No, I don't mean those numbers. I mean the other numbers. The ones
Which
on the
numbers?
right. The conformal anomaly numbers.
Yeah, you just it's just a one-loop computation. It's just a one-loop computation.
Presumably ordinary dimensional regularization.
Yeah, or just ordinary dimensional regularization.
Since you said that the last field rings doesn't have any actual degrees of freedom, what did you use for asymptotic states for those guys?
Oh, in d dimensions it does. Also, it's on the inside. See, in the inside you're in d dimensions, so you're happy. Just do it in d dimensions. So it's formal polarization vectors in some appropriate combination. I mean, this thing is a little bit messy.
You get an epsilon upstairs as well.
Yeah, that's right. Right,
That's really the confusion, because there is a divergence and then there's an epsilon upstairs, and it's a little confusing why there's an 1 over epsilon.
The epsilon upstairs is not actually upstairs. Yes, we got very confused by this. This out here, these gravitons are not in 4 dimensions. They are far away from 4 dimensions. And that is actually crucial. So that's what actually messes up the epsilon counting. You should think of these external states as far away from 4 dimensions. Not of order epsilon. They're just fixed. They're because this object, this counter term, we want it to be non-vanishing. So you see, this is of order epsilon in a sense.
Right.
But we don't, to look at this, we don't want to make it of order epsilon. We want it of order 1, and then we look at the singularity.
But this is worse, because there's an epsilon because of the external legs, but there's also an epsilon because of the number of states that crosses the cut, which is itself of order epsilon. So
No. There's an error. There's a subtle error in that. This point you're making actually it cost us about a week or so of confusion. It's actually not of order epsilon once you put those external states into other dimensions. I mean that's the subtlety. Yeah, we were quite puzzled by this as well. Yeah. Right. So anyway, there's an obvious question here that this divergence that we're finding now at 2 loops is definitely not generic. It definitely has to do with the conformal anomaly. That's certainly a piece of it. And then on top of it, we start realizing that it depends on the details of how you do the regularization, how you're going into d dimensions, okay, with the different states. So actually, you could say the punchline of that is that whatever is going on in pure gravity is not quite as settled as one might have thought, as it's been for the last 30 years. The other place that this is interesting, if you look at n equals 4 supergravity, and you look at 4 loops, there is a divergence. D equals 4. There is a divergence. But this was in a particular way of doing it. We had manifest SU4 symmetry. There's other ways of doing supergravity. Again, these duality transformations. There's an SO4 version, which certainly looks like it has a different structure in terms of these anomalies. Actually, there's a paper from Carrasco and Roybon and Zetlin and Kalish that discusses anomalies. It's in the duality symmetry. There's a U1 anomaly in this theory. And we think that this divergence, at least is what I believe. So now I don't know, I'm just telling you what I believe, that the divergence we're finding, it has to do with the way, with the particular choice that was made of how the symmetries are represented. And then that's what I meant, that there's a divergence. It doesn't really want to be there. It's just that we did something, introduce an anomaly.
Okay. Saying there's a choice where there's no divergence?
I'm hoping that. I'm not saying that. I am hoping. But it's hope based on, this picture that's emerging here. Okay, so maybe.
So what was the conclusion of the conformal anomaly with the count? Was there some particular combination, or what's? I mean, from your list of numbers here.
No. The problem is, so the conformal anomaly. You can play games with the conformal anomaly. We're not so interested in the conformal anomaly. What we're interested in is the effect on the 2-loop divergence. That's a much harder problem because it's a 2-loop problem, and we're working on that now, but we don't have, we don't have the punchline of how this feeds through to the 2-loop divergence.
So you want to take this and feed in the way you fed in Gauss-Bonnet before, but with different numbers and see what happens?
And also add, let's say you add 3 forms, and anyway, you study this thing properly. Actually, the proper study of this is even more complicated because this is just the simple helicity configuration. You really need to study all the helicities to make sure that the divergences don't leak somewhere else.
You use dimensional reduction instead of dimensional regularization?
Well, yeah, the issue of the regulator is, of course, not so trivial. Right. So we use, it's some version of dimensional reduction.
Then you can keep the external momentum in 4 dimensions, I think.
Yeah, that's how these calculations are done. Yeah. To actually address the problem of regularization subtleties is a bit non-trivial because Probably the only way you could really address it is you have to do it conventional scheme. But if you do it the conventional scheme, then you shouldn't use helicities here. And then that greatly complicates things. Anyway, we hope to do that one day, but that's a bit non-trivial. Okay, so anyway, maybe let me just summarize. So I went through examples of magic. And the further I went, of course, the less I understood. By the time we're down here, of course, I don't know exactly what's going to happen. So the examples.
You're saying there's some kind of scale invariance.
Yeah,
Operative.
it's like a broken scale invariance.
Because you're throwing away, you agree to throw away power divergences.
Okay.
And then you're saying there's some laws that
Well, there's well, this trace anomaly, this has to do with this scale invariance of the equations of motion.
Right.
And the divergence seems to be connected to that, or the structure of the divergence. Okay, it's divergent, but it's a special divergence. I think if you want like a clear message of what the scale invariance has to do with, is the scale invariance, okay, it doesn't make it finite, right? But it restricts the form of the divergences.
So Zvi, the N equals 4 theory has a Cossack structure, right? With
Right.
that U1 as the maximum
Yeah.
common subgroup. So remember, can you trace through and see when the anomaly kicks in, so that it could be that free loop is protected by Sold theorems still, because the anomaly only ends up kicking in?
I spoke to Bicert about this at some point, and he said no. So
No, why?
I don't know why he said that, but actually, I don't think that'll happen. The logic is because if you look at the power count, the way the power counting, the way we define the enhanced cancellations, then we agree, just by arguments of supersymmetry with the counting that you had based on the E7-7 symmetry, that there is at 7 loops, if we can draw, I don't know how many, to count out how many there are, but it's actually not this diagram. It's sorry. Anyway, there's one diagram in there. So it's 3, 4, 5, 6, 7. So this type of diagram. If you look at its power counting, then it diverges. It looks like it wants to diverge at 7 loops, and that agrees exactly with what you have, right? And this is exactly the same structure that we're looking at 3 loops in n equals 4 supergravity. In n equals 4 supergravity, it cancels. And we have every reason to believe it'll cancel here as well. I don't think the soft theorems can help you on or their power has been expended. That's what I think, but you're welcome to prove me wrong on that.
I think they've been expended too, yeah. But maybe not for this case. I think that's
I don't think so, but you're certainly welcome to look at that. And if you can prove me wrong on that statement, that would be very interesting. Okay. So anyway, we went through a couple examples on magic. Let me just review. So then we'll be done. So there's color kinematics. Infinities, or 0 instead of infinity. There's various examples I explain. Or maybe, I don't know how to write it. 0 over epsilon instead of 1 over epsilon. Then when you start looking at in detail what the divergence is of the known pure gravity and also n equals 4 supergravity that I didn't really discuss in any detail, you find the divergences look non-generic. And there's clearly something going on here. And then maybe the last point is that there's also a very curious, call it duality anomalies. So this has been discussed in the literature, but I think once you start looking at two loops, the picture becomes a lot clearer.
Can
Okay,
you say a
thanks.
few more words about your mysterious remark about anomalies? You said something like there's an anomaly yet to be named, and it's an anomaly.
Yeah.
Pop up an anomaly.
Yeah. So.
Traditionally, we understand anomaly as something essentially of classical physics that's destroyed by quantum
Right.
computation.
Well, the problem is, okay. So let's go to the conformal anomaly. This, it's not even clear to me this is the appropriate name because this is not a symmetry of the Lagrangian. Okay, but let's call it an anomaly anyway. Once you allow me to do that, which at least there's a 30-year history of people calling it this, then I'm talking about something just like this. And the sign of it, or a sign of it, not the sign, but a sign of it, is it's really got to be a 0 over 0. It has to be of this form for it to come out as an anomaly. Because the way the anomalies work is if there's no subtlety in dimensional regularization, it's just the classical, like you're looking at the cuts. You're looking at some cuts. Maybe there's some cut somewhere. You're looking at the cuts, then classically, if this is a good symmetry, nothing is going to happen. But it's always some subtlety with dimensional regularization that causes the anomalies. And these divergences are exactly of that form. Anyway, that definitely is some mystery to be explained.
Does that explain this duality, the antisymmetric tensor and the scalar?
No. What do you mean by explain? Oh, well, kind of. I mean, yeah. So if you were doing cuts in d equals 4, everything in d equals 4, there's nothing here. There's no difference between these two. Mm-hmm. But when you put this into dimensional regularization, and also because this is an evanescent operator, you want this out into d dimensions, then in fact there is a difference. And not only is the difference a little bit, the difference is a factor of 91.
But from that perspective, is there a scheme in which both of them come out the same, which also
I don't
involves
think
an actual
so.
regularization?
No, I don't think this. I think this is robust. This number, I believe, is robust. Certainly, many people have computed this in many different schemes, including zeta function regularization. These things are robust. It doesn't look like it's... Yeah, we use dimensional regularization. And we get, it's the same answer. And many people have computed in many different ways. So I don't think this is... this 91 is not a regulator.
The calculation involving zeta function regularization would require subtraction of various ghosts to actually keep the number of degrees of freedom the right one.
Yes, that's right. The calculations look quite different. Yes. I mean, if you look at the different papers, they don't look the same at all. They certainly don't look like our...
You're saying that the 91 involves the ghosts are all
Yes, absolutely. Yeah. In fact, this thing is pure ghost, because there's no degrees of freedom.
Well, talking about that, so you said there's nothing there, but of course a free-form potential like that is just what you need for a cosmological constant. And you're telling me that that is actually having an effect in two-loop amplitudes.
Yes.
So is this somehow giving dynamic to the cosmological constant?
Yes. Yes.
Then hope to exploit and solve
I hope
the
so.
problem?
I hope so. Yeah, I hope so. Well, we so far have not actually done the calculations at two loops, but I believe that this is of some deep significance. It's not just some technical thing like there's no degrees of freedom and look at the silly game I'm playing. But in fact, I believe your question is very relevant. At least that's what I'm dreaming.
So if you had to guess, so how far does the 0 over epsilon behavior go? You've sort of given examples, et cetera.
Do you mean like if you go to the next loop order?
For example.
Yeah, we don't know. So Unfortunately, we have like a flashlight so we can peer into the dark and see things, but unfortunately the flashlight is not powerful enough to, look beyond, let's say like the dream that, what you're going to do, what we're dreaming is what you're going to do is, first you're going to monkey with two loops, you're going to make that finite, then you're going to start monkeying, with other, maybe be other operators, other evanescent operators, a whole spray of evanescent operators as you go up in the loop order, and you start playing with that, and pretty much you construct something that looks very, very nice.
Is there a whole spray of evanescent operators?
What's that? At higher? Yeah. Really? Yeah, there's a lot. We haven't categorized them, but I can show you one of them if you're interested. There's an R cubed. There's two, actually you can find this in the Sognati paper. The R cubed, there's actually two R cubes, and those R cubes differ, or they're the same in 4 dimensions. It has to do with an anti-symmetrization of, I think it was 5 indices. So there's some relation to another R cubed, and the difference. No, I don't think so. I mean, it's just for some trivial reason, but it's definitely evanescent. So there's a whole spray of these evanescent operators.
I have a very naive question. Has anybody tried to express all this kind of stuff in terms of old-fashioned Pauli Villar, so it's not possible?
That would be extremely difficult.
That's just not possible.
Yeah, technically it's not possible. The one thing about regulators is this has been studied by other people, Gibbons, Hawking, and Perry in particular.
But you mentioned there are two regularization schemes used here, right?
In a sense, there's multiple, because people do it in different ways. People use ghosts. But Gibbons, Hawking, and Perry, when they were studying the conformal anomaly, they were using the zeta function regularization.
Going back, I'm not sure if you quite finished your statement about the spray of operators and so on, but if you're going to go on to higher loops, etc., what do you think the broader implications are ultimately? If you had to guess or state what your sort of dream is.
Well, the first thing is I think that supergravity theories, especially n greater than or equal to 5, they're going to be finite. Okay. I think that this divergence we saw is just an artifact of the particular way we did it. Right? That's one implication. But maybe bigger dreams.
What do you mean the particular way you did it?
Well, it's because we had, there was a manifest SU4 symmetry, and there's an anomaly in there. There's a particular amplitude that should have vanished, but an anomaly makes it vanish. That anomaly is in the same class.
I understand, but you could have done it differently?
There's a SO4 formulation. That looks different to us. In fact, probably with Radu, we're going to talk about this very soon, to look at this, to try to understand the role of the anomaly in exactly this divergence.
So you conjecture that if you did it with the SO4?
That might be too strong a conjecture. That might be too strong, but the SO4 is definitely different. We could see that just the structure of the amplitudes is not the same as here, and it definitely looks like it has to do with the anomaly. Where exactly this leads, well, we'll find out.
Other questions or comments?
Maybe just wanted to know about the anomaly. I mean, one approach is to look at the effective action at one loop, right? And for instance, by heat kernel techniques, the papers of Vikovisk, Bardisk, and so on. So in that way of seeing, I mean, the 1 over epsilon is accompanied by a log.
Right.
The action is non-local, the effective action at one loop, and you see the trace anomaly as a consequence of the fact that when you rescale the log, you get precisely that structure without the 1 over epsilon. So I wonder. I mean, is one way to compute all these numbers to just do that, the effective action?
These numbers. These numbers, they're identical. So we computed divergence, but It's the same number that when people do the trace anomaly, these numbers you'll find exactly in those papers.
Yeah.
Yeah.
The trace
there's.
anomaly doesn't have any epsilon.
That's correct.
There is
Yes.
There is a non-local effective action.
That's
whose
correct.
variation
Yes,
is
but the two are connected.
connected.
I mean, basically, you can go from one to the other by taking the amplitude and then replace a graviton with a trace.
Because I think that is a clean way to do the. Now, of course, I think you have to impose that you respect some symmetries, like diffs or maybe gauge symmetries for your forms and so on. So, I mean, the anomaly is usually not unique, unless you specify what you want
That's right.
to conserve.
Certainly gauge symmetry.
Yeah, gauge, diffs,
That's right.
the gauge symmetries of A mu nu and A mu nu rho and so on. So, I mean, that seems to me would be the clean way to do it.
Okay.
Anyway, I hope we'll learn in the next year or so. We'll learn a lot more.